Good afternoon, everybody. Mr. Armque back with you for CTS 120. Today we're going to be talking about Chapter 3, Supporting Processors and Upgrading Memory. So two of the more critical components that come about when dealing with building a new machine. We're going to talk about the characteristics and features of both Intel and AMD processors, as they are the two big bads, if you will, used for personal computers. We're going to talk about how to select, install, and upgrade a processor, and compare the different types of physical memory and how they work. We're also going to look at how to upgrade memory, though that will largely be a textual exploration for you guys because it gets kind of redundant having me read it out. Once I give you a rundown of the first way to do it, it's really just kind of a simple exercise from there. So our types and characteristics of processors are following thus. The processor itself, commonly misused term, determines the system's computing power. It is the central processing unit, so it handles all of the primary functions of the machine in a central capacity. Everything has to pass through the CPU in one way or another. Now, modern computing is starting to try and deviate away from that to distribute labor off into GPUs or certain types of NVMe drives that can do some internal calculations of their own. There are two major processors we talk about, Intel and AMD, and they have some very different design ideas and implementation ideas that they will use. So there are some factors that we talk about that affect performance and capability of these machines. So the ones on the left kind of stand alone, and then the one on the right, because it's such a complex one, I gave it its own little box. Processor speed, of course, is going to affect performance. The lithography, the way that it's made, we use usually an etching process to make processors, so that's why they call it lithography, litho, meaning stone, and graph to draw or write, so writing on stone or silicone. Not silicone, silicon, excuse me. Writing on silicone would be very interesting because it would be very rubbery. Socket and chipset. So the socket is the physical interface, and then the chipset is the controlling circuitry that helps to regulate connectivity to the processor. The processor's architecture, does it handle 32-bit or 64-bit instructions? The memory cache, how do we allocate instructions into the CPU? We have these little short-term memory storage units. Security features such as secure boot, other memory features the processor can support such as RAM channeling, integrated graphics, which is a big thing for AMD, has become a little bit more prominent for Intel in recent years, though of course their focus tends to be on just saying, hey, if you want a dedicated GPU, you can go buy one. And then support for hardware-based virtualization. And hardware-based virtualization is pretty crucial in the modern environment of dealing with container-based operating systems. So if you're using an interface like Proxmox in order to test things, or use virtual machines for distributions in a corporate environment, hardware-based virtualization is critical. Software-based virtualization is just way too slow. And then the last feature here, number 10, this is what we call multi-processing abilities. Now, multi-processing just means that we're going to have multiple processes running at the same time, and we're going to alternate their resource requests to the CPU. Let's say I have 4 processes, A, B, C, and D. So I'm going to say, okay, A has a fixed amount of clock time, then I'm going to pass it to B, then I'm going to pass it to C, then I'm going to pass it to D. There is also a process that we call multi-threading. So instead of saying a process, which is a collection of tasks or threads, we're going to take the basic unit of CPU time allocation, the thread itself, and run those in sequence. So let's say that A, B, C, and D all have 5 threads apiece. So let's say that at that point then we go ahead and say, instead of giving A a specific amount of clock time, let's go ahead and divide that time by 5 and say A1, B1, C1, D1. And then we go ahead and cycle through and divide it up so that way we can alternate and be able to accelerate the movement of all processes. We can go ahead and distribute that a little bit more quickly. The faster we do this and the more effectively we can do that distribution, the more that it seems like these processes are actually operating simultaneously. Unfortunately, it's just an illusion. These are actually being processed in a very serial manner, one at a time. Multi-core processing is an extension of this, where we use the physical cores of a system that is using, let's say, a dual-core system, quad-core, hexa-core, octa-core, to distribute the workload of the CPU. Rather than using what we would call a monolith, which is just a single core, we can then rely on different physical operations. And that's actually a pretty common thing these days, is to use a large number of cores to distribute that workload, so that way we don't have to rely on any one single core operating at a particular speed. It's actually much more efficient to use 4 cores running at 1 gigabyte apiece, or 1 gigahertz, excuse me, than it is to have one 4 gigahertz processor. The monoliths don't distribute workload well, and the whole multi-threading, multi-processing task starts to kind of fall apart. So it would actually be even better still, instead of having 4 cores, to have 40 cores, each running at 100 megahertz, because then you can distribute that even more efficiently. Problem with that is that you have to have an operating system that can handle that kind of instruction. Even further than that, this is something that we see with servers, is the dual processor system. This is where 2 separate CPUs share the workload. So if you look into, like, my server here in my office is a PowerEdge T410, and it uses a pair of Intel Xeon processors. And they're not terribly powerful by themselves. I think they're like, 2.4s. But working together, they're able to distribute that workload so that I have, effectively, quote unquote effectively, the access of almost 5 gigahertz of processing power. Now, you're never going to really pull that maximum, unfortunately, but it does help for servers that usually get a lot of requests for smaller tasks to be able to process those efficiently. And that's the thing that a lot of people don't think about. There's a big difference between power and efficiency. Efficiency is really the target, because in terms of lithography, we're kind of hitting a point where we can't make CPUs any smaller in terms of the space in between individual capacitors and logic units. So we have to find a way to make them work together more effectively. So just a little graphic for those who are a little bit more visually oriented. I just kind of threw this together using some PowerPoint shapes, so hopefully it clarifies it a little bit. You can see that there are individual threads. Remember, those are our single tasks. And those tasks, those little threads, get bundled into processes. Those processes are bundled together into kind of what we call the pipeline. And then each individual core will distribute those items. So that thread is still an individual unit of allocation, and it's able to be distributed effectively. So while this isn't exactly the workflow, it would actually go the other way around. You would have processes and then threads, but you would be able to see that there's still this kind of constituent unit principle for each one. So how does this thing work in basic terms? Well, you've got a couple of primary components that always exist in a processor, no matter how complex it is. You've got your input-output unit, I/O. You're going to hear that term a lot. Input-output is just traditionally referred to as I/O. So when we talked about BIOS, basic input-output unit, now we hear I/O with a slash in the middle. We'll hear about that in terms of CPU processing, as well as talking about input-output for peripherals. This is going to handle all of the data instructions that enter and exit the processor. It's the bouncer, it's the door person, the one who's saying who can and can't come in and when they can come in, where they go. The control unit is more of a camp director. They manage activities once you're inside. The arithmetic logic units, which usually come in pairs ever since the original Pentium was released, that's the whole idea of multiprocessing, is that you have more than one ALU inside the core, and that's how you're able to go A and B, alternating the processes. And this is really the brain. This is where the mathematical operations and calculations are carried out. Now, in order to process these calculations, we have to have storage. Now, the way that storage is located lends a lot to how it's termed. If we have storage that's directly on the processor chip, which is the active memory where things are being worked on, we call those registers. These are areas that just hold the addresses, the instructions, the data, and the counters that the CPU's ALUs are actively working on. There are also what we call internal memory caches. These caches operate at different levels and temporarily hold data en route to the CPU, so that way we can streamline the process of moving data in. we have these little vestibules, if you will, these concentric rings of storage that come out from the CPU proper, the ALU itself. So at level 1, that is directly connected to the core assembly. Level 2 is still dedicated to whatever core it's attached to, but is a little bit decentralized. You pass from L2 to L1 in terms of coming from the I/O unit. And then L3 is shared across all CPU cores within the same housing. So if we have a quad core system, L1 will have its primary and secondary cache, and then there'll be a shared cache across all 4 cores. Buses, these, you want to think of them the same way as you would a bus in physical life. You know, if we think about buses in the vehicular sense, it's a means of transport. It is a pathway that connects components inside the processor housing, as well as on the motherboard, any circuit board. The pathway between 2 devices is usually called a trace, and the traces usually make up what is called a bus. So the front side bus of the processor is the front. If it's a 32-bit processor, the front 64 traces. If it's a 64-bit processor, 128 traces. So here we can see a little bit of what I'm talking about. This is a Pentium chip as designed in 1993. So we can see the front side bus being labeled down at the bottom near the center of the image. This is also called the external data bus because it's external pathway to the rest of the machine. And it's 64 bits in width. The I/O unit takes in information from that front side bus, passes it up to the control unit, which then splits the external data bus into 2 internal data buses. So 64 bits of instruction come in the front, pass into the control unit, and are split in half into 2 sets of instructions 32 bits wide. That's what we mean when we talk about a processor's architecture. 32 bits in width means that there's 32 instructions, 32 bits of instruction, excuse me, passing to each ALU. The ALU then passes to the registers. In this case, there are 4 registers. So maybe we can assume that the instructions, 32 divided by 4, are 8 bits in length. And in the hard drive chapter, we'll talk about why 8 bits was chosen as our means of storage. But conveniently enough, you know, that allows us to store anywhere from 0 to 255 in the value of an 8-bit binary word. So that can be, you know, if we had 8 registers, we could then have, you know, twice the number of instructions, but they would be half the length, however you want to distribute it. But in any case, let's say that we have 2 operands. We have, you know, the number 2 and the number 4, and they're written in binary. So it would be a bunch of zeros, and then you'd have a 1 0 for the 2 and 1 0 0 for the 4. The add operator would take up the 3rd register, and then the 4th register would be the memory address where we need to send the result back to. So if we're saying 2 plus 4 is equal to 6, 1 0 0 plus 0 1 0 becomes 1 1 0. We've added them together because we know what the instruction is, and then we send the 1 1 0 result back to memory address, you know, 0x99b, whatever it is, just off the top of my head. The process of handling those instructions from external data bus to register and then back again is pretty consistent. But the ALU is the fastest component. That doesn't mean, however, that it's automatically going to empty out the second it processes any one thing. So if we have a queue that starts to form to be able to process information inside the processor, we need to have a place to put it. And that's what the memory caches do. On the left-hand side, you see where it's labeled internal memory cache. That's L1. So if you want to think of it that way, that's your deal. If you want to think of the registers as L0, because most computers tend to start at 0, that is not a bad way to look at it. So here's a little textual representation of what I was just talking about. Something that is not something I brought up yet is the concept of the clock speed. The processor operates on what we call a system clock. It's usually a quartz oscillator that vibrates at a particular frequency when you pass voltage through it. That's how overclocking works. We amplify the voltage that passes through the system clock, and it makes the rest of the system run at a faster pace. Now, the system frequency, the processor frequency, is not a raw number. It has to be derived. So the system bus operates at a particular speed, and then based on the the amplification that we use through the voltage, we generate what's called the multiplier. The multiplier is used as a scalar for the system bus frequency. So let's say we have a system that runs at 800 megahertz and it has a 4x multiplier. 8 times 4 is 32, so that's 3200 or 3.2 gigahertz. Just a common pathway by which we do that. In order to have the same result with a 2x multiplier, we would have to have twice the frequency. Or if we had twice the cores, then it varies out. It's all ratios. But the idea is, how fast is your system bus and what is your multiplier? The multiplier can be affected by clocking as well as the number of cores. Processors sold today contain ALUs and registers that contain either 32 bits or 64 bits of instruction. You're almost never going to see one that contains 32 bits now. Simply because the instruction sets are considered to be outdated. There's much more complex things we can carry out with a single instruction in 64-bit space. Legacy support does exist, especially for older automation, as we've talked about in previous lectures. Now, today's processor architectures fall into the category of an x86 or an x64. Most of us will talk about the x86 only in conjunction with a hybrid processor. These can handle 32-bit or 64-bit instructions natively. This is handy if you have a dual boot system to where you're maybe running a 32-bit version of Windows on one partition and a 64-bit version on the other, or if you're running a 32-bit version of Windows that communicates with a 64-bit version of Linux. Or a 32-bit version of Unix that communicates with Mac OS, being able to have two of those on the same hardware. Just depends on your particular configuration. 64-bit processors, also called IA64 or x64, can only handle 32-bit instructions by simulating 32-bit processing. The way this is usually done is to say, well, I can handle 64-bit of instruction, but let me go ahead and just take it in as 32-bit instead, but I have to have the 64 bits. So I'm just going to add 32 zeros to the end. So this means that even though 64-bit processors are able to handle more complex instructions, if they're simulating 32-bit processing, they run at half their usual speed. Now there are some mathematical tricks we can use to fiddle about with this, but in general, simulating 32-bit operations don't tend to mean that 32-bit operations run twice as fast. It just means that they're able to run, period. So here we see our quad-core processor mocked up with each core handling 2 threads. So an octa-core processor produces 8 physical threads. Each of those threads can alternate logical cores to where they could handle 2 logical threads per physical thread. So here we have CPU number 1. Let me grab my pointer real quick. So we've got CPU number 1 here in the top left. See there? If we imagine that this has a physical thread 1, physical thread 2 going to the ALUs, each of those ALUs could then potentially process a virtual system of 1A, 1B. So each of these would process 4 threads in the logical form, which means that we would have 16 threads total logically. Now again, this expands if you talk about like a hexacore or octa-core processor, but that's how we try and make the most of the processing abilities that we already have. So here's just kind of a rundown of memory cache for L1, L2, and L3. The memory controller is something that's important to think about. This will often provide a significant increase in system performance because rather than memory just coming in based on what's called a FIFO system, first in, first out, it's able to actually prioritize and queue information based on an assigned priority from the hardware. So here we see the quad-core processor. We're peeling off a layer, if you will. We're going in. We see the memory controller up top. We see our primary cores 1 through 4 with their L1 cache contained. So you can think of this kind of like each individual core is one of the Pentium diagrams we saw just a little bit ago. The L2 cache, as I said, is dedicated to each individual core, but is considered physically separate, kind of like having a detached garage. And then L3 is shared across all cores within the processor assembly. So let's look at Intel. let's look at some specific stuff to the manufacturers in question. Intel has actually both processor companies have what we call families that identify different groups of processors that are set together for particular functions. The Intel Core series is pretty much their major offering at present. The i7 and i9s are made for high-end desktops and laptops. i5 is a good mainstream, middle-of-the-road kind of operation. And i3 is considered entry-level. If you recall from your labs, the i3 is what we use for our trainers. The Pentium processor is designed for entry-level desktops and laptops. We don't see it very much anymore. Atom processors are BGA sockets, and they're made for low-end desktops, notebooks, and laptops, as well as home entertainment systems. Celeron processors, which when they came out were very nice because that was the first time they had incorporated the network controller into the processor assembly, are now used predominantly for low-end portable devices, netbooks and laptops. So Celeron, when you hear Celeron, think mobile. So the Centrino technology that was attached to Celeron interconnected the processor, chipset, and wireless network adapter. Now, there's a lot of server processors they deal with now, the Xeon, the Xeon Phi, and the Itanium. That's mostly because Intel has always focused on the corporate level. AMD is much more of a hobbyist style CPU, and that's not to say that they're not high quality, it's just they've always focused more on the individual rather than organizational technology. Now, there are versions of the i3, i5, i7, and i9 that do work with servers, but that's not the primary use for which they're designed. Let's talk about AMD. AMD is usually much more popular with, home, tech tweakers, people who like to play, video games, especially ones that are very computationally intensive, and people who like to build things for, 3D rendering or other, intensive projects at home. That tends to be more of the people who lean towards AMD because they are really geared towards customization and project-specific operations. Current AMD processor families would be for desktops, the Ryzen Pro, the Threadripper, especially for the very high-end stuff, A-Series, A-Series Pro, and FX. For laptops, we still have Ryzen and Ryzen Pro, as well as A-Series and A-Series Pro. And for servers, the Epic and the Opteron. Not quite as popular, but definitely still strong contenders in their own right. The FX processor here we can see is a little bit older, it's 2011. This is an AM3 socket style processor, and it has 8 internal cores. AMD was one of the first to really focus on the whole multi-core situation, as well as including integrated graphics. So how do we pick a processor for a machine, be it an upgrade, a repair, or a new scratch build? Technicians are called upon to do all of these things, be able to set it up brand new out of the box, be able to fix something that's not working, add a processor to a multi-processor system, or upgrade something that's already there. It's important in this case to know how to match a processor to a system and to install a processor on the motherboard, the actual physical process as well as the planning. So let's make sure we have a processor that the motherboard is designed to support. Next, we need to make sure that we have a processor that meets general system requirements and user needs. So the features to consider would be the best processor we can find, the processor's ability to multitask. We're balancing power and performance with that of the entire system. To use a car metaphor, you can't put, a big V12 into a Yugo or a Volkswagen, a little Volkswagen Beetle. You have to make sure that what you're putting in isn't going to essentially just leave everything else in the dust, because at that point you're wasting money. You start bottlenecking very early, meaning that there are components that limit your ability to maintain strong functionality. Read reviews of the processors you're considering, of course. Look for reviews that include comparison benchmarks, and look at the negative reviews. I think that's the thing that's most important for me is, look at what they're complaining about. If it's stuff that you feel is really negligible, then maybe it's a little bit more to discount. But if the negative reviews are not terribly specific, maybe consider that they are being paid detractors, that sort of thing. The internet is a very powerful tool, and companies will definitely manipulate that to their own ends. When processors and coolers are boxed together, you may have a heat sink that's already applied with thermal compounds, so just be aware of that. I always prefer to buy an extra tube just in case. I don't like being without it in case there is a problem where maybe it gets smeared or it's too little or it's too much, being able to clear that off effectively. So here we can see this little pre-applied square on the bottom of the package. So to install an Intel processor, we have 9 basic steps. We have an ESD strap to ground us, anti-static gloves if possible. Make sure that when you're replacing the processor, the system is powered down. That should seem pretty simple, but of course we always have to make sure that we are methodical in our steps. Unplug everything, drain the system. The socket, if it's a new motherboard, will have a protective cover. Go ahead and pull that off. Open up the socket by pushing down on the lever and lift away using the lever, the socket leveler. So you're going to press down, away, and then let it lift up, and you'll push it backwards to open the plate. The load plate is just a metal, it's not quite a ring, it's a square or rectangular frame that covers the edges of the CPU to hold it in place evenly. It's what we call a zero insertion force socket. Now we're going to take the protective cover from the processor, holding it with our index finger and thumb. I usually use my middle finger just to give it a little bit more. I can kind of steer with my index finger. And let's align the processor so that the 2 notches on the edge line up with the posts embedded on the socket. These are registration marks. You have the notches, you have sometimes a little dot or kind of a golden colored triangle on one side in order to make sure it's aligned correctly. Once we've got it set into the socket, it should just kind of gently rest on it if it's Intel. The pins are only if we're dealing with AMD. Once it's in the socket correctly, let's go ahead and gently push the lever back into position, lowering the load plate and locking it in place. So here we can see an LG A1151 load plate being opened. You can see that the bar there kind of pulls it back with it because of how the metal is bent into that kind of arch shape. You can see here the registration marks using the little right angle corner in the bottom, well, bottom right if you were facing the socket, but on the top left if you're facing the image. Then you can see the notches in the top right and bottom right. Here we see those marks a little bit more clearly. You can see on the corner of each side of the processor, top right, bottom left, there are little circles, whereas in the top left, you see there is a triangle kind of pointing. And then you have the little notches that allow you to indicate which way the processor should face. Now, for installing a processor, we need to install the cooler assembly. We can't run a CPU without cooling, so we need to understand how the cooler posts work. If they are the little twisty pins, as they would be with Intel for the most part, be aware of that. I will say that some of the newer ones, especially like the Wraith tower coolers for AMD, are kind of similar to this, except instead of using pins, they now use spring-loaded screws. Make sure that the cooler posts are understood by you. Make sure you're aware of how they work and how they're going to mount, because you don't want to have to lift up the CPU quite a lot. Once you've put the thermal compound down, the thermal compound paste, which may be pre-applied, you may have to peel off a little plastic sheet to expose it. Make sure that it is down firmly and that you do not move it after that point. You don't want to smear it around. Kind of defeats the purpose. Now, if you have a heavy cooler, or if you have a cooler that's particularly tall or awkward, there may be a plate that fits underneath the motherboard that has to be anchored in place. This is just a backing plate, simply because the printed circuit board may be thin enough to where eventually, if it's put upright, the stress and weight would cause the board to bend, buckle, or snap. Then we can go ahead and install the cooler. If lighter coolers have locking pins, make sure you're aware of whether or not they need to be turned clockwise or counterclockwise. Once the cooler is mounted, just kind of give it a little wiggle and see if it has any play. If it does, figure out why and eliminate it. It may be that one of your locking pins wasn't turned all the way, or one of the screws, if you're using like a Wraith cooler, wasn't tightly screwed down. Now make sure that when you're using screws that you do not over tighten, because you don't want to apply uneven pressure. You want to make sure that it's snug, but it's not going to, snap the second it starts moving or expanding. Then we go ahead and connect our power cord from the fan to the motherboard. There'll usually be a fan header pretty close by that says CPU fan or main fan or something similar. If you're using water cooling, then this obviously is not entirely applicable, but you can treat the water block very similar to how you would treat the cooler assembly. You'll have your thermal paste, you'll have your mounting materials, and then basically you'll have to deal with your inlet and outlet piping. Go ahead and check UEFI to make sure that your system recognizes the processor, and maybe run it for about a minute or two, just kind of without load, to see that the temperature is nominal within range. That's where you're going to want to check your documentation for your CPU to make sure that it's operating at the correct range. So here we can see a graphic of the mounted processor. You see the thermal compound there in the center, that little dot. Some people will use an X. Some people will use just a big dot like that. I don't recommend any shape that leaves a gap. You want it to be a continuous application, because this is trying to avoid air pockets. So that's what we want to make sure that we're not introducing. You can see here the holes on the motherboard. This is where we would attach the cooler assembly. In certain cases, you may see little posts that come up through these holes, and that's because that backing plate usually has little stems that the locking pins will then thread into. Here we see the assembly plate I was talking about, just kind of that backing plate to make sure that the board isn't damaged by a heavy cooler or awkward positioning. Here we see the pins that will connect to the fan, just to the left of the RAM slot. And here we see a different angle on the same one, providing a connectivity point. Something I want you to notice when you look at the left-hand side of that connector and the port on which it's going to sit is that there's a little plastic tab at the front that aligns with that pair of tracks on the connector itself. That helps you to make sure that you're facing the pins in the correct direction. You're not accidentally misaligning them. So now we can see that we have the CPU installed. So if we look up near the top, near the middle, we can see the CPU core voltage reading at just over 1 volt, which is pretty common. About anywhere from like 0.98 to 0.11 is usually pretty common. Motherboard temperature is reading at 26 degrees Celsius. So if we divvy that out, it's a 9/5 plus 32, I believe is the calculation. So 126 multiplied by 9, I'm sorry, 26 by 9 should be about 234. Then divide that by 5, that gives you just about 47. And then if we add 32, it gives us just under 80 degrees. So this is running really, really cool. The fan's only going at like 700 RPM, so that must mean that this particular system is running very, very low on load, or has a very efficient cooler. Normally you'll see something that's like closer to 90 to 100, especially in the lab, just because our trainers are a little bit more low end and the coolers are not quite as efficient. AMD processor is pretty much the same. The only thing we're going to make sure of difference is if we look at step 3, verify the processor pins are setting slightly into the holes. That's because with an Intel processor, you have a land grid array, which means that you have flat contact points. With an AMD processor, you have PGA, where you have pins that actually insert into slots in the socket. So you can see those pins there, not the easiest because it is kind of face on, but you can see in the socket that there are little holes that are going to slot in. But you see it's also the same concept of the lever that'll help lock it into place, and in the bottom left of the CPU, the pin face, you can see the little yellow triangle to orient which corner is supposed to go where. You see the alignment positions. These are missing pins that will only sink in one particular direction or other, because they're not, they're basically 360 degree calculated to not have any overlap. There's no way to put the processor in without damaging it or forcing it by just setting it on top in the incorrect way. Here we can see a slightly different locking mechanism for a cooler. Instead, here we're going to use a cooler clip. It has 1 clip on one side, 3 clips on the other, and it uses leverage of a bar that goes across the heatsink to hold it in place, as opposed to the lock pins. Now, this is an older AMD system. As I said just a little while ago, the newer ones, the Wraith, like tower coolers and stuff, they screw into posts the same way that an Intel set would. For laptops, it's a little bit different. Now, before we replace anything on a laptop, we always want to do kind of a cost-benefit analysis and figure out, is this going to be worth it? If the laptop's under warranty, let someone else handle it. Or in certain cases, it may actually be less expensive to replace the laptop, which is, for some people, it's really hard to believe. But it's kind of like it's cheaper to buy a printer than to buy ink. But what a lot of people don't think about is that the ink that comes with the new printer is like a third or a quarter of the size of a full-size cartridge. So it all comes out in the wash. Now, if you do decide to replace, let's make sure that the CPU is supported. Follow the service manual. Usually it means that there's going to be a cover that you'll have to remove to get to the processor fan. You may have to have more complex disassembly, especially for things like gaming laptops, just because they have to be put together like puzzle boxes half the time. Make sure that when you're removing a CPU that you do lift it out straight up. If you have like a suction tool that you can use instead, like a little suction cup, or a really squared off pair of plasticized tweezers or extractors, those can be used as well. What you don't want to do is try and push it down on one corner to lift up an edge, simply because that's much more likely to damage the pins. When we put in the new processor, of course, we want to follow the same steps we would on a desktop, make sure it's registered correctly, and then go ahead and put your thermal compound on. So we see here just kind of a breakdown of where everything is sitting. We see the SODIMMs on the bottom right corner. Just above it's the processor heatsink with the CPU below it. Processor fan above that. There's a little copper tube going between them. That is going to contain a very volatile liquid that very quickly turns from liquid to gas when exposed to heat. That means that the pressure will increase. It'll move towards an area of lower pressure, which is usually going to be where the fan is. It'll cool the metal, and then it'll condense and flow back. So you set up a convection current in order to enhance the cooling. To the left of the SODIMMs, you'll see the hard drive, usually a 2.5-inch model, and to the left of that, you can see the Mini PCI Express wireless card. That is a half-height Mini PCI Express. And the little black and white wires attached to them are the antennas, which you want to be very careful with them, because if you accidentally dislodge them, they are a huge pain to remount. So here we can see the different screws that hold the fan and heatsink assembly together. Again, we want to make sure that we're following the service manual if at all possible, so that way we don't accidentally knock something loose or lose a piece. Here we can see the processor removed from the socket. This one in particular has a retention screw, so instead of a lever, you can see that little flathead screw on the right-hand side of the socket. Basically, when you put the processor back in, you will turn that screw 90 degrees in order to lock the pins in place. So now we've talked about CPUs, let's look at a little bit of RAM technology. RAM stands for Random Access Memory, and that's because it temporarily holds data and instructions used by the CPU. RAM is a dynamic technology in that it constantly is losing its data. The voltage kind of drains away as it's present, and it has to be refreshed several thousand times per second. There are a couple of variations of DRAM we talk about: dual inline memory module and small dual inline memory module. So SODIMM, or small outline, is what we use for laptops. We may also see what's called a micro DIMM that's used on a sub-notebook computer, but those are becoming a little bit rarer. So here we can see a number of different options based on, I don't know what they searched in particular, but we can see here that we've got some different RAM of various capacities. We see some DDR4, DDR2, got some 288-pin DDR4 from Dell, so we've got some fancier stuff from Kingston, a couple things from Ripjaws. DRAM tends to vary based on the pin count. So essentially, if we have pins on both sides of the DIMM, we have a dual inline memory module as long as those pins are independent. If the pins are on both sides and they are conjoined, meaning that you basically flip over the stick and the pin on the other side is connected to the one that's parallel to it, that is a SIMM, single inline. And then we have what's called RIM, which is a proprietary model made by a company called Rambus. Their claim to fame was working on the hardware for the Nintendo 64. They were very similar to, I want to say, DDR2. I think they had 184 pins as well. So the variations tend to change based on how wide the data path is for each module and how data moves from the system bus to that module. So here we have a number of different types of RAM. We've got SIMMs, we've got DIMMs, we've got RIM, we've got DDR class 1 through 4, and you can see there's all these different qualifiers of what makes them them. So traditionally a DIMM has a 64-bit data path and previously used to run asynchronously. Synchronous RAM, or SDRAM, runs in concert with the system bus, meaning that it is clocked to the same timing, so it didn't have to constantly be regulated as it was delivering information to the CPU. Now, the D in DIMM stands for dual, as I said, but there's also another D that we look at, which is DDR, double data rate. So when DIMMs were first mooted, the idea was that the system clock had a rising and falling tone. It was a sine wave. So you would have a peak, drop to a trough, and then the next peak. And we would measure from peak to peak or trough to trough. We would have to measure to the same point on the wave in order to calculate what was called the period. So the period of a wave was from one low point to another or one high point to another, whichever it was. But because there was a low and high point in a single period, we were then able to identify, hey, well, what if we did a signal at the top and the bottom? So now for every period that passes, we have transmitted data twice. So that's what doubled. We sent data rates twice per period instead of once. DDR, basically, every time a new version comes out, is faster and uses less power. Now they have to make sure people aren't trying to fit new chips in the old slots, so they have to make them a slightly different size, change the notches, change the orientation. How do we affect DIMM performance, capacity, etc.? Okay, well, the number of channels they use. We'll talk about channeling in just a moment. How much RAM is on one DIMM, or the term that we learned in lab, density. The speed of the DIMM, and the error checking abilities thereof, as well as buffering for use in server situations. So single channel DIMMs are where the memory controller accesses one DIMM at a time in order to process memory. There's one RAM stick being accessed at once. Dual channel is where we say, okay, we're going to access two DIMMs at the same time. So if we have 4 slots, a single channel would be 1, 2, 3, 4. A dual channel would be 1, 3, 2, 4, and alternate back and forth. So in order to clear the entire bank of memory, it would take 4 cycles for a single channel and 2 cycles for a dual channel. Triple channel boards can access 3 DIMMs at once, but in a 4 configuration system, 4-slot system, we could only have 3 DIMMs active, so we had to leave 1 port empty. Quad channel is where we can access all 4 DIMMs at once. And if we have different levels of DDR, that implies the different levels of memory channel support. Now, in order for our channels to work, both the motherboard and the DIMM have to support the technology in question, and traditionally these will be color coded. So if you see like black and gray or black and blue on your memory slots, they alternate. So like blue gray, then another blue gray. Excuse me. Now, to set up dual channeling, it is recommended that we have the same size, speed, features, and manufacturer. If we don't, they will run at the fastest speed that both of them can support, which means that if you have a really fast stick and kind of a moderate stick, they're going to run at moderate speed. Triple channeling also has to have the same matching, and again, remember, we can only use 3 sticks or multiples of 3, so 3 or 6. So here we can see our dual channel construction. Memory controller is talking to the RAM. We've got RAM channel 2, 1 black slot, 1 gray slot, and then RAM channel 1, 1 black slot, and 1 gray slot. What we would say as A1, B1, or A2, B2. So here we can see our channel A slots are spaced out from one another, as are the channel Bs. We can see here that with the ARM laid down, that the 4th slot in this configuration is empty, so that's a triple channel configuration. And traditionally, if we're going to use quad channeling, let's go ahead and have 8 memory slots, because in order to use quad channeling, we can't have all 4 next to each other. They need to be spaced out, so we have to have 4 channels with 2 groups. So we have to have, channel A 1, 2, 3, 4, channel B 1, 2, 3, 4. We can't do A1 through 4 with no B. In order to ensure optimum performance, of course, we should always check our user manual. Here we can see an X399 gaming motherboard with 8 DIMM slots at the top and bottom of the CPU slot. And then we can see that the quad channeling is supported by the documentation because the slots are all the same color. So unfortunately, that doesn't tell us much in terms of channeling. Now, how do we calculate the speed of our DIMMs? How do we figure out what a memory speed rating is? Well, we traditionally use the units megahertz, and then we have a term that we call PC rating. Now, there's an inverse relationship between what we call cycle time and frequency. Cycle time, of course, is the amount of time it takes to move data into or out of the RAM chip. So 200 megahertz on the RAM stick would be equivalent to 5 nanoseconds of cycle time. Now, 5 nanoseconds is 5/1000ths of a millisecond. So 1 over 0.005 is 200. PC rating is a measure of the total bandwidth of data moving between the module and the CPU. In order to calculate that, we have to know the data path. Well, DIMMs are known to have an 8-byte data path, which is 8 bits in a byte, so 8 times 8, or 8 squared, is 64. For example, if we have a DDR4 DIMM running at 3000 megahertz, we will then multiply that by 8, by our data path, and get 24,000 megabytes per second, or 24 gigabytes per second of transfer speed. That would be an expressed rating of PC4 24,000. PC4 just basically tells you that it's using DDR4, so PC3 would be DDR3, PC2, etc. Now, error checking. Error checking, or ECC, is going to be where we identify an error based on a comparison. So there's a code that's inserted every time the RAM is written to that is compared, and if the code does not match the necessary value, whatever comes through, then it's able to say, hey, there's a problem, and I'm going to go and fix it. But if there are 2 bits, essentially the error detection for the second bit takes up the same sequence that would be used for the correction in a single bit. So in application, we would add an extra 8 bits in order to process these little checksums, if you will. So it would make a 64-bit DIMM, a 72-bit module. Parity is very much the same. It also included 8 extra bits, but they were distributed per memory chip. So if you had 8 8-bit chips, all of them would have an extra 9th bit in order to process that extra information. Odd parity was where we had to make sure that in every 9-bit sequence we had an odd number of ones. If we had even parity, we had an even number that had to be there. The parity error deals with the number of bits conflicting with the parity type used. So an odd number of ones in even parity, or an even number with odd. Here we see a couple of options that use ECC to enhance fault tolerance. So you can see that that's an advertised aspect of the stick. And it has to be noted that we don't want to mix ECC and non-ECC RAM because it will not function. There are also technologies called buffering and registering that can be employed. So buffers essentially just hold the data and amplify the signal before the data is then written to the next device. So kind of like when you're watching YouTube and a video preloads a certain segment of itself, so that way the playback is smooth. That's the whole point of a buffer, is to smooth out transitions between a period of fullness and a period of emptiness. We want to try and avoid running the motor dry, as it were. So a buffered DIMM will exist in 2 primary configurations. In normal buffered or registered memory, we just buffer the control lines, which basically make sure that the impulse control signals are correctly being submitted and accepted. In fully buffered memory, the data lines are also buffered and all transfers are performed in serial. So modern buffered memory traditionally operates in fully buffered form because most transfers are done in serial anyway. We'll talk about this again a little bit later on when we get into dealing with data transmission for hard drives, but serial transfers are much more stable because they have to be transitioned in sequence. You have to send A, then B, then C, then D. If you send A, B, C, and D running shoulder to shoulder, if there's any disparity or desynchronization that occurs, the whole message slows down because we have to wait for the other pieces of the message to arrive before we can interpret them. So if we send them in serial, no matter how fast or slow they arrive, we know they should be in the correct sequence. So that allows us to use faster and faster transmission frequencies. Registered DIMMs, RDIMMs, which are not the same as RIMs, by the way, use a storage register between the memory controller and the RAM itself. Now, the reason they do this is because it's less electrical load on the memory controller, and it allows a single system to remain stable with more modules than they would have otherwise. So let's say that we have a RAM stick that currently operates at 1.5 volts, and we have 4 of them. If we use a registered DIMM, we're then able to cut the voltage to 1 volt instead. So now we have an additional 2 surplus volts that are designated for our RAM sticks, which means that we can then implement a further 2 modules. So now, with the same power consumption and stability, we can access 6 RAM modules instead of just 4. And then, of course, we can get tricky with timing and things like that to produce even more dramatic effects in certain systems. An unbuffered or standard DIMM has no buffer or register support and does not rely on any external device for correcting or augmenting its data signal. We also talk about the concept of latency when we talk about memory, how quickly something is able to transition into or out of the RAM to its intended destination. So we talk about column and row access strobe, CAS and RAS. Both of these terms refer to the number of clock cycles it takes to read or write a column or row of data from a memory module. Now, because most programming languages, especially things like assembly, machine-based languages, are column major, meaning that they read columns before rows, CAS latency is used more often. Now, lower values are better, and they indicate a shorter completion time. Latency is all about delay. So if we have a high latency, that means that there's a lot of delay going on, not something we want to see. Advertising will often provide a series of timing numbers to identify the overall speed of the RAM stick. 99924 or 55515. This is going to give you what we call the CAS latency first, the CL, and then you'll see the RAS to CAS delay. You'll see the RAS precharge and the active to precharge delay. The TRAS, the very last number in a 4-sequence code, tends to be the one that most people pay attention to because that is the largest number. It gives you the overall idea of from when the RAM stick becomes active to move to the precharge for the next cycle is how many nanoseconds. So in this case, it would be 9 nanoseconds for CAS, 9 to transition from RAS to CAS, 9 to precharge the RAS, and 24 to go from active sequence to precharge in terms of nanoseconds. So the last number is always going to be close, though not necessarily the same as the number, as the sum of the numbers that preceded it. In laptops, we also use what's called DDR3L. Now, this is very close to registered memory. It uses low voltage instead. And it's not going to be used to expand the amount of memory it uses. Instead, it's going to use the lower voltage to reduce the power consumption, thereby the heat and waste energy that might otherwise be consumed. Make sure we're only using the type of memory the laptop is designed to support, and make sure that the pins, as well as the notch orientation, keep us from inserting the stick incorrectly. So again, do your planning phase. Make sure you pay attention to what you're doing because you don't want to A, get hold of RAM that you can't use, and B, accidentally damage a slot by trying to force something in the wrong way. Let's talk about upgrading memory now and how that's done. To upgrade memory just means to add more RAM. RAM can solve a lot of problems, whether your system is running slowly, applications are refusing to load, system instability, and then you may actually get a message from Windows saying that you have insufficient memory to perform a task. So when we're adding memory to a computer, we traditionally fall into 5 questions. How much RAM do I need versus how much I currently have? What type of memory is currently present? How many and what kind of modules can I fit on my motherboard? How do I select and purchase the right modules for my upgrade? And how do I install the new modules physically? How do I actually put them into the motherboard to make them work? So let's take these one at a time. In general, how much memory do I need is however much you can get. You want to consider the limitations of your motherboard, processor, and operating system. Your operating system needs at least 1 gig for pretty much anything current for a 32-bit installation, but as there are very few 32-bit installations around, we're going to say the minimum is 2. With Windows 10 Pro, we can support up to 2 terabytes of memory, and I believe that carries over to the Windows Server versions as well. Windows 8 Pro can handle up to 512 gigs, half a terabyte, and Windows 7 Pro can handle up to 192 gigs. I've never seen that employed on a desktop, but I have seen it done in servers, so it just depends on what configuration you're talking about. As far as the limitations go, as far as maximum memory that's more attainable, a 32-bit Windows installation can only handle 4 gigs of memory. It comes into some addressing problems. So as you can see, if you're talking about a 32-bit version of Windows 7 or 8, you're only going to be able to shoot between 1 and 4 gigs. So that definitely limits you a little bit. So what type of memory do I have? Well, let's open it up and take a look. Now we can find some of this information using UEFI. We can use things like Speccy. There's a tool from it's ccleaner.com to be able to identify the different aspects of your RAM. Number one being the model, if you can find it. Examine your motherboard. Make sure that your motherboard supports whatever type of memory channeling you want to use, as well as the memory. Sometimes you'll see what's called a memory QVL on the support website. And if you still can't identify the module after all of that, you can take it into a good computer parts store for confirmation. Note they say good. You definitely don't want to take it to a shady kind of computer shop. Here's just a graphic to show you what a DIMM label might look like. So I'm going to grab my highlighter and we're going to take a look at some different items on this list. Now, as my highlighter is not angled, this might not look quite right, but we'll see how it goes. Let me grab the pen instead. Maybe that'll be a little bit better. Okay, so first we're going to look at 4 gigs. That's the density of the stick. It's PC4, so we know that it's DDR4 RAM. It runs 17,000 for its class. So we know that the PC rating is 17,000. If we divide 17,000, here, I'll put it over here, 17,000 over 8, and we get 2 here, 16,000. 1,000 left. And then we go ahead and start eliminating as we go down. So we've got 1, 6, 6, just about. 2,166, probably going to be the megahertz of operation to give us the 17,000 rating. Well, you can see our timing numbers over here, 15, 15, 15, and then our active to pre-charge 36. We can see our voltage is 1.2. Here's our model number. Here's our manufacturer. And they even included a handy UPC scan that we can see there. We want to take a look at the motherboard as well. Here we can see that it says that it is a Prime Z370P from Asus. So that gives us the ability to identify what motherboard we have and make sure of the compatibility before purchase and installation. Now this is a little bit long, but I'll try and get through it quickly. The idea is we need to pay attention to what type of memory functionality we want to have. Now not only do we need to know how much the motherboard can hold, but if we want to support different types of channeling, we have to be aware of how to configure it. For dual channeling, we need to make sure we're using the correct slots to make sure that we're channeling it correctly. So, A1 to B1, A2 to B2, etc. If we have a triple channel system and we have 4 slots, we need to know which one to leave blank. If we're doing dual channeling with 4 sticks, we want to make sure that we're dual channeling correctly there, making sure everything's matched up. And then if we're doing quad channeling, obviously if we've got 8 slots and 4 sticks, we need to make sure they're spaced correctly. If we're using triple channel DIMMs, we have to rely on what's called SPD. Now this is something that we use for every configuration, but especially for triple channel because it has to make sure that all of the various aspects match. With dual channel, we're able to pair things off, so that means that we could have one pair that matches, one pair that's close, but they match one another. So we could have two pairs that are close together. Kind of like a family having two sets of twins. But in this case, man, we need full triplets. We got to make sure that the speed, size, voltage, and data path all match. And the part of that that does it is what's called SPD, serial presence detection. So that'll actually declare all of those aspects. Used to be an old RAM, you had to go in and declare it manually. You had to type it in. Meant that there could be possibly some problems with timing. So here we can see the DDR3 slots on a particular motherboard, and you see that one of them is left in black, the other three are in blue. So in this point, what we would do is we would populate one black, one blue for dual channeling, the second blue for triple, and then we would leave the fourth one blank, able to move that into, I guess, 4 single channels if the fourth slot is populated. Some memory systems will actually allow you to do triple without having this indication. It'll just have black and blue, black and blue. It just depends on your manufacturer. Again, read your documentation. I cannot say that often enough. Now, if your exact match is not available for mixing memory, just make sure we're not mixing things like unbuffered or unregistered memory with buffered or registered memory. It doesn't work. Match the manufacturer if you can. If not, most of the other metrics should be okay. I just wouldn't expect optimum results if you mix manufacturers. If you have to mix memory speeds, which is the least recommended, you will see a significant decrease in at least one of your sticks because they will run at the slowest speed that they can all agree on, essentially. Use a website to research your purchase. Make sure that all of your modules will be matched to your motherboard. There's a couple of them that'll allow you to go directly to the motherboard site, or that they'll let you put in what motherboard you have and then tell you what's compatible. Crucial is pretty big on that. So here we see Crucial screenshot for typing in your motherboard. The graphic got a little bit cut off, but you can see down at the bottom below where it says need help, Asus motherboards, Prime Z370P. So that'll match the one that was in the demo unit we looked at earlier. So to install the new modules, we treat it like any other component. Same thing we did in the teardown lab. Make sure you wear your ESD strap, full power discharge, don't handle the edge connectors, don't stack them, and make sure you're orienting them correctly using the registration notches. We'll go ahead and remove the existing DIMMs by pulling out the support arms. Depending on your motherboard, only one side may open. That's okay. Don't force the other side. You don't want to break anything. Use the notches on the edge connector as a guide to slot the DIMM down. When you push it down fully, the registration notch should slide into place and the arm should pop up and clip into the sides of the stick. Then you can kind of gently tug upwards and it should not come loose. When you power up the system, SPD will launch and go ahead and check the memory present, and UEFI should verify what you have. So here we can see the clips on an open slot versus a closed slot, and you can see that they sit absolutely flush when they're correctly seated, and they sit at an open adjacent angle when they are not. Here we can see the technician putting firm but gentle pressure against the entire length of the stick in order to make sure that it is correctly seated. You can see that the pins line up, you can see the orientation notch lines up, and then they will lock into place once the arms close in. Now, upgrading memory on a laptop is pretty similar to upgrading memory on a desktop. We're just dealing with smaller stuff. So make sure you're not voiding warranty. Make sure that you need to check for a suitable and authorized part. There's a couple of different locations where you can get those parts most of the time. The days of the proprietary memory and stuff like that are well behind us, thank goodness. But you may run into it on occasion. So again, just do your research. Our general steps are to make sure we can decide how much memory to upgrade ahead of time. I would say if you don't really have a budget as an option, like if you're doing it for a client and they're like, I need this memory, then obviously we need to look for the max out that the motherboard supports. If not, then we need to find a balance between performance and cost. And then if we're the client, obviously we have a lot more flexibility, but if the client is not you, then we obviously want to propose a couple of options and let them choose what they would feel is the best. Go ahead and procure the memory. We'll order it from wherever. I got my last set of RAM from Amazon, of all places. I've kind of started checking out normal retailers in conjunction with
more specialized places, simply because sometimes volume really does make it up, and you can get a really good deal by buying it from a place that just sells a ton of RAM as opposed to having to go through some specialty shop. Once you get it, go ahead and verify, make sure that it is the correct stuff. Again, check your documentation, and then install it using the steps we talked about previously. Make sure we're matching the type of memory to the type the laptop supports. Again, I've said it at least 4 times in this presentation. Check your documentation. Write it down, double check it, because there's nothing worse than sitting down to do the installation. You got your workspace cleared, you get everything hooked up, and it's like, oh, this doesn't fit because it's the wrong model. So be careful, especially if you're buying any kind of budget RAM that doesn't really have a clear name of what it is. The descriptors will sometimes have a lot of jargon and really long model numbers, and it becomes difficult to keep track of what it is you're actually buying. So that is chapter 3. Hopefully you have gotten some enlightening information about motherboards as well as memory, being able to optimize RAM and different aspects of the memory system, as well as how the CPUs and RAM interact on the motherboard. You know, how to upgrade, why we should upgrade, when is it best to pick, you know, the fastest or the most expensive, when is it better to go for a little bit of budget. As always, if you have any questions or concerns, you can always email me at jearmke063@cfcc.edu. You can, of course, see me in my office in the MB building, or you can contact me via my Google Voice number at 910-239-7814. Text is best. So hopefully you have a wonderful rest of your day, and I will see you next time.